This week, the speaker is Dr. Brenda Frye, who at least I see in the top left of my grid, but I don't know if everybody gets the same order. And you'll see her in a few seconds. So Brenda did her PhD thesis at Berkeley, and then she went on to postdocs at Lawrence Berkeley Lab with Saul Perlmutter and Princeton University, and held positions, lecturer faculty positions in Dublin and at the University of San Francisco before moving to the University of Arizona in, I guess it was 2011, where she's been since. So Brenda's an expert in galaxy formation and evolution, and particularly using clusters, the gravitational lensing of clusters as magnifiers. And so today she's going to tell us about new views of galaxy cluster laboratories. Take it away.
Yes, thank you. Let me share my screen. Okay, can everyone see this? Oh, sorry.
Just before you start, I'll mention what we discussed, that Brenda is happy to have questions during the talk. So I would suggest, I will try to keep an eye on it, maybe use the raise hand thing before you interject, and we'll try to interrupt in a smooth a fashion as we can. So we'll give that a try, okay? Sorry about that.
Yes, that's right. I'm absolutely happy, and I'll be even asking some questions so we can try to make this a little more interactive than just sitting there, listening, watching a TV program. Okay, so I'm very happy to be here. I hope that I wish that all of you and your families are well and healthy at this time. Good. So this talk concerns using the Planck telescope, actually, in a completely new way to do astronomy, to identify high redshift galaxy clusters. And it also concerns using the Planck telescope in this new way, which is to color select sources that are also classical giant arcs, gravitationally lensed sources. So hopefully this is enough already to pique your interest. And yeah, I should say that overall the talk will consist of these 4 parts. We'll open up with a bit of a motivation for why we care to study galaxy clusters, and we'll discuss the Planck sample, and then we'll finish up with this irresistible introduction to this relatively new phenomenon of high magnification events that occur right on the cluster caustic, right on the Einstein rings, essentially, of galaxy clusters, which we call caustic transits. So the work that I'll show today had contributions from many people. The 3 I want to highlight are the 3 people listed in bold, who are students, two of whom were undergraduate students when this work was done. So let me see if I can move along and test the advance. Good. Okay. Sorry. Okay. Wait. Okay. Now we got it. Okay. Right. So I'll start with my summary slide. By doing a color selection, okay, and not by the SZ effect, but just by doing astronomy with Planck, searching by colors, we were able to uncover ensembles of galaxies at high redshift, essentially redshifts 2 to 3. By this same approach, we were also able to detect sources which were brightened by factors of 10 or more individual infrared galaxies using Planck. I'll present all of these results. Then finally, we'll discuss 2 different ways to detect these new caustic transits, which are interesting if you're not in the lensing field, just because they can involve magnification factors that are factors of 100 greater than any that we can see in normal cluster lensing of galaxies. Okay, and I think that has a real future in high resolution observatories such as JWST. Okay, so now we'll start. So galaxy cluster laboratories, why do we do it? Well, massive galaxy clusters lens all objects in the background. so that the background objects are brighter than they would be in the field. Using this technique, we can successfully detect objects all the way out to the epoch of reionization, and even higher. And we can study these objects very well also near the epoch of the star formation rate density peak of the universe, or cosmic noon, with redshifts 1 to 3. These galaxy images of these background sources can be so bright that we can even use them to basically serve as probes to analyze the intervening intergalactic medium towards the object, much in the same way that is done towards quasars classically. Okay. So one example that demonstrates a variety of these concepts is the case of Abell 1689-71, which I show here in the upper right. What you see, and I can test, everyone's seen my cursor? Yes, okay, that's my laser pointer, effectively, okay. So here, what you see here in the center is the brightest image of a triply imaged galaxy at redshift 4.9. It is in fact brightened up by a factor of 10 by this foreground cluster, which you can only see as a result of these few bright orangey type yellow objects, which are cluster members of Abell 1689, something Michael knows a lot about. Okay. So this image is really small. So I show it again. I show it here as a zoomed image with a 1 arcsecond bar in the upper left. This object is really quite bright. It has an I-band magnitude of 23. And you can use this as a background source. So what we did is we went and obtained a very high signal to noise spectrum of this source. We were curious basically to test our understanding of the H1 in the surroundings of this galaxy. So typically quasars are bright, intrinsically luminous. They also ionize large regions in their proximities called proximity zones out to 8 megaparsecs or even more. They're wonderful for studying the standard IGM, but they're not very good for studying the H1 near to them and surrounding them. Galaxies, on the other hand, are much less luminous. And in fact, these lensed ones are bright as a result of the lensing. And so we can use them really to try to get at what is the H1 structure closer to the sources and surrounding the sources. So to get straight to the point, when we take a very deep spectrum of this object, which you see right there, it looks pretty much just like spectrum of any other redshift 4.9 galaxy. It has many of the same features. It has stellar continuum. It has stellar continuum. It has Lyman series break, strong interstellar lines, high and low ionization, and strong, in this case, strong Lyman alpha emission lines. But if you look a little bit closer, and I remind you of the redshift, it has a really exceedingly deep absorption just shortward of the Lyman alpha. So here is my cue here. If you were to put masking tape over the x-axis and show it to you again, you might certainly still correctly identify this as a high redshift galaxy, but you might assign to it a redshift that's higher than it really is because of this excess absorption, especially if you're used to looking at these types of sources. So we set out to do a really straightforward analysis to try to see if there might be really an overdensity of H1 here, just by separating, sort of dividing up this region of the Lyman alpha forest into five different wavelength bins, and then we computed just the H1 opacity relative to our SCD continuum fit to the starlight. And we show that here on the right is the Gunn-Peterson effect of optical depth as a function of the redshift. Indeed, we uncover excess H1 absorption surrounding this source relative to the standard IGM, which is shown by the other points. So it appears that this region is H1 overdense, and we infer from that it probably is surrounded by an H1 overdensity, that this may be a structure that is currently building up a lot of its stellar content. Okay, so that source was an example of an image family, which is a single galaxy, which by effect of strong lensing can appear in multiple locations in the image plane. The galaxy can appear photocopied, essentially. We call that an image family or image multiplicity. In all, we found 30 such examples of image multiplicities in ABL 1689. So let me just show you one of those. I won't show all 30, although I find it interesting. But anyway, so here is now a larger picture of ABL 1689. Again, if you see my cursor, we can point to all the different objects here, which have the same color, which have the same K correction and are at the same, all in the lens plane, the same redshift. They all have the similar colors. You can't see very many arcs, so I can highlight a set just here. If I zoom in on those regions within the circles, you can show one example of really two different galaxies. We call them object 1 and object 12, okay, which are imaged multiple times in the image plane. So you can imagine taking this object 1, which looks like a grain of rice, and this one like a fluff of cotton, and rotating it to achieve this image, parity flipping it to achieve this image. This is what we think is a central demagnified image, and so on. So part of what I think is a really enjoyable aspect of studying clusters is to identify these image families. Okay, that brings us to the second really important aspect of lensing, which is to study the dark matter. Okay, so I think we probably all know that is the lens equation that we use, which relates the source, image, and deflection angles. For a simple point mass, it's probably already really intuitive that this deflection of light past the source goes as 1 over the impact parameter. Right? The closer the impact, the smaller the b, the bigger the deflection. But what you might not know is that for the case of the singular isothermal sphere, that alpha is a constant for a given lens and for a given source, and depends really only on the properties of the lens. So what I mean by that is, for any object well behind the source, it will all have more or less the same deflection angle. Well, let's go back to the intuitive bits. You can imagine that the magnification factor for galaxy images in the background is a strong function of redshift, right? With a peak right at the Einstein ring radius, which we call also the tangential critical curve. Okay. And if there are sufficiently high surface mass densities, then we can get the strong lensing effects, the large boosts in brightnesses, and multiple images. Okay, so I show in the lower left one of the first sort of cases of image families at high redshift. This one shows 4 different images of a galaxy at redshift 4.040, 1, 2, 3, and 4. There was also cluster elliptical, which we subtracted off so that we could better uncover the fainter light from these sources. You can see this is sort of 3 components in the star-forming knots of this galaxy. Sort of a compact one, light one, and a yellowy one. And the same thing, compact one, yellowy one, and anyway, 3, right? And if you were to sort of think of this maybe as a kind of Morse code, then you would imagine that you see this pattern of 3, and you see the same pattern of 3 on this side. You see, we call that, we say there's similar parity there. And that means that these 2 images fall on the same side of the critical curve. Let me explain this in more detail for the panel in the middle here. Again, we're thinking about multiple images. If there's a source, okay, which is quite near the optic axis here, and that source is falls well within the Einstein ring, then we can expect that in this case there can be multiple images. In this case, there's a simple double image of an image I plus, which appears just outside the Einstein ring, and an image I minus, which appears at a slightly lower magnification just inside the Einstein ring. Okay, and in fact, they're called plus and minus because in this case, these images would be on either side of the Einstein ring, so there would be a parity flip in the actual image, which you could detect by the morphology. Okay, so some of you are saying right, and others are really not understanding. So let's go to the right-hand side here and show you another really nice image. This is of the cluster CL0024. I can tell you that there is an example of a multiply imaged object there, and there is an example of a parity flip within that object as well. Can anyone find it?
Can find the image, but at the
You
moment
can.
I
Okay.
can't see which ones are parity flipped.
Okay. So which is the image?
Muted mic.
Okay. The blue things that look a bit like a sort of a theta symbol.
The blue things that look like a theta symbol. That's right. Okay. Yeah, that's right. Exactly right. So look at the one on the bottom, which I've oriented, this way for a very particular reason. This one on the bottom is the I- image that you see down here. And you can see that there's a kind of a theta symbol, but there's a bit more of a concentration of light just there at the bottom, okay? Now, if you look up to this image here, which is covered by my participant list, or this one here, you can actually see that there's a parity flip in the way the theta is represented, okay? And that's one sort of interesting way to tell if you want to surprise your friends and family to know where the Einstein radius is relative to those images. Okay, oh, super, okay. So now we'll move on to the part 2, Planck selected galaxy clusters. That's interesting, okay. Look, there we go, okay, all right. Yeah, I got it, okay, super. Right, so basically when structures form, like massive galaxy clusters, in this case at really high redshift, okay, when they form, they release light into the universe. And this we call the extragalactic background light. So the most primary contributor is the cosmic microwave background. And the second most major contributor is the cosmic infrared background. So we set out to try to find peaks in the cosmic infrared background, which correspond to these mass peaks, okay? In particular, we wanted to use a survey that sampled all sky, which is what led us to this Planck survey. It has many things that don't go for it to do astronomy. It's low aperture, really low resolution, and so on. But Planck is all sky. So all sky surveys are only good to find the most maximum, most rare sources and to pick them out. So this was the purpose of using Planck, was to find the most rare peaks, the very brightest submillimeter sources from the sky that are also red, and so potentially at high redshift, okay? Where does this submillimeter light come from? Well, this comes from dust reprocessed light. So we think as the structures form and as the star formation turns on and the star formation becomes very, very vigorous, that the dust, which also forms in large amounts, absorbs all of this starlight and re-emits it thermally. This thermal emission comes out then in the rest-free far infrared. See in very simple terms this type of picture here. And then the redshift at which this far infrared black body, pseudo black body curve redshifts into the observable passbands of Planck is 2 to 3. So we kind of hardwire a redshift range. Many of these clusters, many clusters are found at redshifts higher than that and lower than that, but our sample is sensitive to this redshift range 2 to 3, which also corresponds to, as I said earlier, the star formation rate density peaks. So these are really objects that we think we're catching at their highest star forming phase. We identified a couple thousand objects, and then we were able to follow them up at higher resolution to see what it is that we found. In fact, I don't know about you, but just based on what I said, it's not really obvious what you would find. And in fact, I was probably about 50% sure that we had found anything interesting at that point. But the Herschel results turned out to be really, really interesting. So let me show those, not for the 228 sources for which we got data, but just for 2. So here's a really nice protocluster, which we now have a redshift for. It's at redshift 2.5. We didn't know it at the time, but just given the Herschel data, which we show in 3 different bands here, you can see something that was very typical of the vast majority of our Herschel cases, which was that we see about 5 to 10 individual objects that separate out from that sort of within that single unresolved detection of something using Planck. As we would expect for several simultaneously star-bursting galaxies, all in close projected proximity. We were very happy to see it. It wasn't unexpected, but we now have a really pretty nice homogeneously selected sample across the available sky. And I'll spend a little more of this part discussing more about this sample. I should mention at this point, though, that in a small handful of cases, we did not see several objects emerging from this single Planck detection, but that we saw that the object remained compact, even at higher resolution using Herschel. This was, a little bit surprising. Planck cannot detect individual infrared bright galaxies, of course, or we would have done it a long time ago. So what is it that we're seeing here? Well, maybe Planck can't do that, but Planck can detect an individual sub-millimeter bright galaxy that is also boosted by a factor of 10 or more by strong gravitational lensing. So we started to investigate this sample as potential giant arcs identified using Planck. Let's get back to this sample, though, for just a couple more slides. Okay, here's just a few of these protocluster sources you can see on the sky. They include some of our Herschel data shown here by the yellow contours. So these sources are selected to be the very brightest sub-millimeter sources by their dust reprocessed light, selected by color to meet the peak, basically, of this thermal distribution. We expect them to be selected on the basis of their star-forming properties. Some interesting questions are, is this the star-forming finale for these galaxies? We're measuring star formation rates of between 1 and 2,000 solar masses per year within the Herschel beam. Now we know that even that breaks up into a small handful of sources. We're not expecting that's the star formation rate per source, but the star formation rates are enormous. Okay, they should be exhausting all of their available gas in a very short time period, another 100 mega years, and turning off to perhaps become the cluster member galaxies of the future. But as we'll see, perhaps it's possible that they can be longer lived as well, as they may need to be if they want to be truly extremely massive CD galaxies. One interesting question, which has some debate going on also, is are these sources really going to become the Abell 1689? Are these the progenitors of massive lensing clusters? Okay, well, let's get back to the Herschel data here. If you take just the Herschel beam and you say, what kind of star formation rate do you expect if you consider that given a Herschel signal, which falls for this particular protocluster within this black, this is the Herschel detection right here. If you just assume that there's one object inside of this wide Herschel beam, which is not true, but if you just assume that, then we can come up with a star formation rate of between 1 and 2,000 solar masses per year. If you instead can isolate these sources and you determine the star formation rate independently and sum them up, you should get the same answer. Okay. So we went ahead and we put on here are the protoclusters for which we have secure spectroscopic redshifts. We measured these in the redshift, by the way, using multiple CO rotational transitions. And we find that compared to this particular less successful survey called Carla and some others as well, that our sources, our protoclusters, tend to have higher star formation rates than the others. This is in a plot adapted by Noiro et al. 2018. There's no boasting rights that one has here. We simply selected our sample by its high star forming properties, and that's what we got. Okay. These other groups selected their protoclusters by other properties. So we don't expect that we're really finding the entire protocluster population, but only one with those properties. So if we look again at this one particular protocluster, which is kind of a special one just in this sense that it will be observed using JWST in GTO time. So we wanted to understand more about it. This cluster, Planck G191, also has Spitzer data. We acquired Spitzer data for 82 sources, which appear by these red contours that you see here. We then used the prescription of a recent paper by Retura et al. 2018, which relates the richness of the galaxy density in Spitzer IRAC imaging to a halo mass in order to make halo masses for 3 of our sources, which we put here on this lower plot. Okay, what's also very interesting is that we think that these galaxies at redshift 2 to 3, as Deckel and company point out in 2009, which have halo masses expected of clusters, 10 to the 12 solar masses or greater, are capable in some cases not only of having this sort of hot gas component expected at virialized masses, but also to have the ability to have cold flow accretion, so that there might be a means to fuel these massive galaxies so that their star formation is longer lived than the 100 megayears that we would expect if this starburst was a single event. These are open questions and ones that we're trying to work on and to address with future data. To close this part of the talk, let me just show a photo album of all of our Herschel sources here that appeared as part of our press release in 2015. Okay, now I'll move on to show you the giant arcs. As I pointed out, in just a very small handful of cases, in fact, of about 11 of the 228 cases, we did not find protoclusters at redshift 2 to 3, or protocluster candidates at redshift 2 to 3, because we have not investigated them all. But we found just single objects at redshift 2 to 3, single submillimeter galaxies. We call them dusty star-forming galaxies, which are lensed by a foreground cluster that was not detected using Planck. Okay. And we were able to get HST imaging for 6 of those 11 sources, which I show here on this slide. Okay, in all cases, we were able to identify the dusty star-forming galaxy, which is one of the brightest sources in the submillimeter sky. As you can see here, they're rendered into really quite modest giant arcs here in these near-infrared images, because already there is quite a lot of dust extinction that that makes them, in a sense, less special to look at it in the near-infrared. Here's one here. There's some here, which are really only revealed inside of these little circles I'm drawing here. Very hard to see them. Here's a nice bright one here, which is a triply imaged object of a single galaxy, triply imaged family. Here's one here, which is actually a beautiful partial Einstein ring, which we were able to resolve using ALMA. There's one here, which is actually a galaxy merger of 2 unrelated sources in progress, and we have another one here, which is very faint. Okay, so again, remember, Planck cannot detect one field infrared bright galaxy. Okay, so these sources are all clearly not in the field. They're all highly magnified. Okay. It means that they are selected, in this case, by their extreme brightness. And that means that if we put them on a plot, along with other lensed submillimeter galaxies and other submillimeter galaxies, that they should be brighter. So we make a plot here of the 350 micron flux density as a function of redshift. And indeed, we see that about half of our sources, of the 11 sources, seem to have higher flux densities than the others that we could draw from the literature. Now, because this was an all-sky survey, the sources that we found were the brightest on this all-sky survey, and therefore should be the brightest that will ever be found. So we also didn't really succeed, because there are a few that other people found that are just as bright or brighter. So we're still looking at those. What I should say though is that one of our sources, this one here, which I point to, G165, is extremely bright and has a very large Einstein ring. So it is of interest to us, and I'll spend the whole rest of this part of the talk discussing only this object here. And, oh, there it is there, not the others. I'll show you a couple slides concerning this photometry, spectroscopy, the lens model, and then present a puzzle. So we need to gather all the clues from these first three parts before we'll be able to think about the puzzle. Okay, here's now the full HST image showing this G165 galaxy cluster. This is the first HST imaging of this source. You can see the cluster members again, which make up the lens, shown in this case as these sort of whitish type of sources. And you can see some arcs. Let me zoom in on this region here to show you the kind of richness of this arc structure. So here you see a lot of different bits and pieces of arc. Let me try to give you just a brief tour. Look at this yellowy, maybe orangey source here, this fluff of cotton, and this elongated source. And note that these three sources appear also on the other side of this axis. It's this one, and that one, okay? So the axis is really the Einstein ring. Just by seeing this type of mirror structure, right, which tells us that there's opposite parity. Remember the discussion we had earlier on in the talk. We know that the Einstein ring must pass right through here, and that these images are on opposite sides of that Einstein ring. Just for kicks, I should point out as well that about 20 arc seconds away, there is a third image of each of these here. Meaning that these three background galaxies appear as three different images, image plane. In all, we identified 11 different independent image multiplicities here, and those we used to place strong constraints in the lens model. But the most interesting one is left out. What about this one here, DSFG1? This is one of the brightest sources for tens of degrees in any direction in the submillimeter, and yet it has this little, modest image here. And no counter image. I mean, when we take all these other 10 image families and try to predict where the counter image would be for this particular dusty star forming galaxy, it should be right there. Do you see something there? Does anyone see a counter image there?
A little bit of off-center fuzz, maybe?
Yeah, thank you. I always thought that, but I had trouble convincing anyone else.
Well, I may be guided by where you put the circle.
You are guided by where we put the circle, yes. But there really isn't anything convincing there. There's so much background and noise from the halo light of the cluster members and so on. What we really need is longer wavelength data at high resolution, comparable to HST. But we've already pushed the wavelength limit of HST, and we don't get JWST just yet. So what we did, we found we're able to get excellent high resolution K-band imaging from the ground using laser guided adaptive optics. We use this brand new imager you might not have heard of. So the LBT is the Large Binocular Telescope. I don't know if you're familiar with it. There are two 8.4 meter apertures which sit on the same mount, rotate together, act like a pair of binoculars. So it's the binocular telescope. Lucy then is our imager and near infrared spectrometer, and Argos is the component which allows us to make these ground layer adaptive optics corrections. I was lucky enough to propose to observe this source and to be there during the commissioning. So I show you this image here, which I took during the commissioning of the source. It is absolutely amazing. If you take a look here, you see what look like two green beams shooting up into the sky. These are the artificial stars. In fact, there are 6. There are 2 constellations of 3 beams each. You just cannot resolve these 2 beams into 3 and 3, as here are. So each of these 3 beams piggybacks on each of the apertures and produces artificial stars. We're then able to use those stars to take out the atmospheric distortions. And this was a tremendous aid, and even with this beautiful data set, we find that it still is subject to the usual problems with observing in the near infrared from the ground, which is that the background goes all over the place. It varies tremendously, even over timescales of minutes. And you can see we took these data even under good conditions, similar conditions, 6 days apart, and still we have very different levels of background. We also see that just the full width half max of the point sources is really noisy and varies over this same time period as well. So it really took my graduate student, Eugene Chen, and I a full summer of working on this data to very, very carefully and iteratively peel off the background. And we found we were able to go through 3 stages of iterations from the sort of initial stage to clean it up and clean it up more until we had really, really nice imaging. So I want to show you that right now. Okay, voila. So this is our K-band Argos image of central portion of G165. It really is beautiful. We see a lot of different sources here, which is one of the better images that you'll see of a cluster field in the K-band prior to JWST. Okay, this is as close as we'll get anyway. Okay, and what's very interesting is that we detect really, really well, and a little more brightly, in fact, right? We get a very nice detection of this millimeter galaxy now. It looks a little more interesting than it did even in 1.6 microns. And more importantly, we detect its counter image. That's a little hard to see, so let me show it again. Here you see the familiar 2 fields that I showed you just in the previous slides. Now this middle one here is what I want to draw your attention to. This is the one that shows HST plus the K-band data. Now this source stands out a bit more. It's not really that much redder, it's just 2.2 microns, but we see now it's very red, stands out as the reddest object in the entire field that we have. And not only that, but the other extremely red source is right there. And I don't know how well this shows, but there is clearly a beautiful red source right at the expected model predicted location for the counter image. So we have landed a secure detection of this counter image. That was very important because it's really hard to get the good constraints that we need to make a robust lens model. Those constraints include spectroscopic redshifts. And of the 11 arclit families we have, there's a spectroscopic redshift for 1, which is only this one here, 2.2357. And we really needed to have a counter image in order to anchor that down. Oh, I jumped ahead of myself. Okay. With that in mind, I'll spend just a little bit of time talking about the spectroscopy. We found that although there was some spectra that we could pull in from the archives, there weren't enough spectra of cluster members even to get the redshift of the lens. So we had to go and get our own spectroscopy. So we got spectroscopy of many sources, which are shown in blue here on the left, including 18 cluster members. So the spectroscopy is shown here. These are really nice data, which give unambiguous multispectroscopic feature redshifts. Also that, again, here, the histogram of redshifts is, you see just here, there's a nice strong peak at redshift 0.351, which is our measured redshift for the cluster. As well as, if you see here, this is sort of one of the important clues to the puzzle that's coming up. We see a pretty tight relation of the cluster members. Pretty steep, nice tight relation there of all the cluster members hovering around redshift 0.351, with some extension out here, but it's less. Okay, so based on these sources, we don't have 100 redshifts yet, but we have 18. We could measure a dynamical mass that puts this source above 10 to the 15 solar masses within the field of view of HST. So it's a nice massive cluster showing a lot of lensing evidence. Okay. Hit number 2 is that this is a double cluster. You can clearly see here when I show you the center, that there is a mass concentration both above and below this line. This line is just simply drawn at the midpoint between what I take to be the two centers of these mass concentrations. And when I did that, I found that I got, luckily, about half of our spectroscopic redshifts, half of the 18 were above the line and half below the line. So I asked the question, can I figure out the cluster orientation? Which half of the cluster is behind the other? Okay, and the answer was inconclusive. We don't know. We don't have enough information. Sometimes it's not so easy to do. I sort of pretended to guide your thinking a bit by drawing this little yellow slab, which essentially sort of points out that perhaps this side of the cluster here, this northeastern one, is behind the southwestern one. But that's only if you ignore these 2 points here. One would only ignore those because they're emission line sources. And so not really what you expect of normal cluster galaxies at a redshift of 0.3, unless they're newly infalling galaxies. And so perhaps undergoing more star formation and their motion is not yet subject to completely to the gravitational well of the cluster. Inconclusive. Not obvious anyway, okay? The lens models, I'm not going to spend too much time on those. Talked about them a little bit already. We use the time-tested light traces mass model, which relies heavily on providing strong lensing evidence. We have a lot of strong lensing in the cluster, so this seemed to be, for us, a good way to go. We identified the cluster members. We just pulled them off of the cluster magnitude diagram that you see here. This is hint number 3 of the puzzle I'm about to give, which is that there's a very tight correlation of the cluster members that you see here, given by the red dot, given by the red stars. This is actually what you expect for a galaxy cluster. It usually shows that they all have similar colors, even though they have a range of magnitudes. And this we call the red sequence. It's used for sort of a classical way to find cluster members. But interestingly, as usual, it is really a nice tight connection. We also identified the arclet families, 11 distinct ones by their similar colors, their morphologies. Sometimes the image flips, as I pointed out, but still similar morphologies and model predicted locations. We would take a family out and ask the lens model where it would expect to see counter images, and we tried to check our model that way. To make a long story short, we did manage to get a nice model for this cluster, which recovered the bimodal mass. Okay, so now I include here this very interesting Einstein ring, the critical curve, which basically was generated by our lens model, shown by this white contour. It doesn't have the usual perfect circle that you see in your textbooks. If you don't study lensing, it's probably what you carry around in your head, but this is a double cluster here. It does do the interesting things we expected. It passes through some of these sources here, for which the images appear on opposite sides and so are parity flipped. Also, it's same here. And it passes straight through the submillimeter galaxy detected by Planck. I also just point out somewhat randomly another one of our arclet families in great detail. This one is a single galaxy that it's imaged in 5 locations in the image plane, 1, 2, 3, 4, 5. I like this one because we were able to find counter images that were on the opposite side of one of the main mass concentrations, which gives us some additional leverage on the lens model. Okay. So the puzzle, okay. This cluster, G165, is a low luminosity X-ray source. Well, that's putting it politely. It's undetected using ROSAT anyway, and it has a detection by Planck as Z effect of that is less than the 2.5 sigma level. So how can it have such low X-ray luminosity? One would one would infer from that, it would have a very low mass, for example, in it that is completely at odds with our measurement of the dynamical mass, with our measurement of the lensing mass, which I didn't go into, but which is also large, and with our measurement of the caustic mass, which we also measure to be high. So what is going on? What is this cluster doing with its hot gas? That's the puzzle. I'm happy to take suggestions, but maybe in this case, we should wait till after. Okay. So what we can propose is that perhaps this object is a double cluster as we expect, and that it is merging. Not only that, but it's not merging it's not in a really advanced merger state, which is post-core passage, as you might expect, at all, because most of our understanding of merging clusters is in this sort of post-core passage phase, such as the bullet cluster, which is very high X-ray luminosities, and so on. But this is clearly not true. This is really an X-ray quiet type of case. So what if these two clusters could be on their initial infall, and in such a way that there would be also an extremely high entropy level, which may counteract somehow the high energy component. It's a puzzle. Okay. And finally, for the last part of my talk, I wanted to discuss a bit about caustic transits. The first caustic transit was discovered in this cluster field, the one that you see here. If you don't study the field, you don't need to memorize it, but it's called MAX J1149. I think the reason why these nice discoveries were made in this cluster field is because it's a Hubble frontier field as well, so it got special attention with Hubble Space Telescope with very deep imaging that we're conducting several bands. Not only that, but there's even a little bit of a cadence set to it to try to identify objects such as supernovae. And in fact, to sort of set up our discussion of caustic transits, indeed, supernovae were discovered using in this source that were lensed. The most famous example of a lensed supernova ever was really in this source. We call that supernova Refstel. As you see here in the very middle, there were 4 images of the same supernova. This is a single supernova at redshift 1.52, okay, which was lensed by this whole cluster, which is at a redshift of 0.5, into these 4 images. Not only that, here's the 4 images down here too, if you want to see them. Not only that, but not all 4 images appeared at once, of course, because there are different geometric paths. One image would appear, and then there's actually time to make a prediction for when the next image would appear. And these predictions were made and were correct. So we know we have a pretty good understanding, at least, of the lens model in this particular part of the cluster. I bring this up as an introduction because of this beautiful deep data and the nice cadence. It meant that it was also the first cluster for which we might expect to find other serendipitous discoveries. And this one is really nice. So let me show you now the image in the lower left. Okay, in the lower left, see, it was in 2014 that the image right here in the blue circle, which we call Icarus, was first detected. And then it was in April of 2016 that we noticed that the image inside this circle brightened by something like 30%. Okay, that was interesting. But then 6 months later, on October 30th of 2016, a second image appeared inside this red circle. You don't see it now because I'm not showing all these images, but there was a nice image also filling this red circle. Then 2 months later, on January 3rd, 2017, the image in this red circle disappeared and the image in this green circle appeared. And this image stayed present the entire time. Okay. What we think is happening is that there's an individual star at a redshift of 1.5, okay, which is boosted in brightness on account of its proximity to the Einstein ring, which is right here given by the red solid line. And because of that ultra-high magnification, And because of a microlensing effect, we're able to see, we think, a second image of that same star right here within the red circle. Then we think, owing also to the fluctuating caustics, we're able to see a magnification minimum, which demagnified the stars and brought up either a third image or the first image of a second star within the green circle. In any event, we're not used to having this kind of excitement in the fields of galaxy clusters, which are supposed to be these really long-lived things. So this is all very new and interesting to us. We call this a caustic transit. Okay, but this method of detecting the caustic transits, if I should say, is beautiful. It worked well. It was the same method that was used to find supernovae, of time tested and very nice. And it continues to be highly successful, so that's fantastic. It just simply just bothers me slightly because it seems really risky. It's a sit and wait kind of technique. And I don't always know how I can, sell that idea to attack. We may or may not find something we don't know. So there's a second way also to make detections of this caustic transits, which are predictable and for which we expect to see them on time scales of a year. I'll spend the last few minutes of the talk just describing that. Okay, here we have another nice case of a set of arcs which bridge the critical curve, the Einstein ring. You can see them all right here, and here's the Einstein ring right there, perturbed by these galaxy cluster members, but there it is. Okay, we also see the mirror symmetry on opposite sides of this cluster critical curve, right? As I kept saying, these sort of parity flips that we expect when images appear on opposite sides of the critical curve. Now let's just see if we can understand this new concept for how to make this caustic transit detection. I'm going to introduce some fancy animation here. Let's rotate this so that we see what looks like a face to me, a sort of forehead, two eyes, a nose, and a mouth, and a bow tie. And I think I can illustrate this best by putting up a picture by Picasso. So just as Picasso never really favored symmetries, perfect symmetries on either sides of his axis here, the same is true here. If we were, for example, to take the flux ratio of images of the right eye and the left eye, or the right nostril and left nostril, or the bow tie, or whatever, if we take those ratio of fluxes, we certainly would expect for that not to be 1, because there are differences. There are subhalo structure, there is not exactly perfect geometry, and so on. But whatever that flux ratio is, it should be steady. It shouldn't change with time. If that flux ratio does change rapidly with time, then we know that there's some other reason to explain that. Okay, and this would be that there's an actual change in the source. So let me go ahead and move on to that one next. The reason why we think we can see these individual stars at cosmological redshifts is because we have not only the cluster lensing component here, providing a factor of 10 magnification, but also we pepper this plane with microlenses. Okay, they can be stars, stellar remnants. As Joe Silk pointed out to me once, they could even be large globular clusters. They can be Omega Centauris, really, which would still be 8 to 10 magnitudes dimmer than anything you can see and still compact. Whatever they are, they're peppered here in the image plane, and the combination of the two produces these high magnification factors that you cannot achieve with cluster lensing by the halo mass alone. They produce these beautiful, rapidly changing caustics in the source plane, which enable one to achieve these high magnification factors up to 10,000. So let me just show you very briefly the result. If you take this nice face, eyes, nose, and mouth, and bow tie, we'll just center on the bow tie right now. Let's focus on that. If we just consider putting down these image ribbons over these arcs and making a kind of illustrating these image ribbons here in 2 different bands, and we can go ahead then and just consider how the surface brightness, the flux changes along the long axis of the arc, and you can see indeed we have quite an asymmetry there. One might expect that to happen, but that these asymmetries can be caused by microlensing. If it's meant to be, just a boost in brightness, it could be caused by dark matter substructure. Okay, but if we're going to see any rapid changes in this flux, okay, then we would attribute that only to the microlensing interpretation. Okay, so to make a long story short, can I put that there? Oh no, it didn't appear there. Okay, to make a long story short, this feature brightened by 30% within 2 years, between 2012 and 2014, which to us rules out any change in moving dark matter substructures. The feature is also extremely blue, likely a blue supergiant. So we think by putting our best models down that we are able to detect a blue supergiant at a redshift of 0.94 in this arc. That just happened to be detected because of the rapidly changing caustic structure as a result of the microlensing. Okay, and we think that it experienced a boost in brightness of about a factor of 200 to 300 times its ordinary brightness, and allowing us to make the detection. Okay, and we expect to make these detections every year. All we need to do is find the right set of arcs which bridge the critical curve, and then we should expect to be able to predict to find these types of events. This is powerful because we can use this to study individual stars at high redshift, to potentially put together initial mass functions directly by watching stars cross the caustic one by one by one, not by the motion of the stars at the source, but by the changing caustic plane in the lens. Or that we can even access the very most distant sources, which will probably be unavailable to us in the field or behind clusters otherwise. So with that in mind, I'll leave you with this image again of the Planck-Seminar galaxy. Okay, remember this really nice red image we got using LBT? It turns out that the Einstein ring indeed passes right through it, we think now. And in that case, one can ask the question, are these two star-forming knots images of the same star-forming region? Is it possible that we can also measure a caustic transient in this redshift 2.2 source? In fact, we measure a star formation rate of several hundred solar masses per year. There should be plenty of stars there. Food for thought. So in closing, I want to sort of highlight a couple of these sources. This is the G165 source I talked so much about, okay, which is a relatively understudied galaxy cluster that was found using Planck by color selection and not by the SZ effect. As I mentioned when I discussed the puzzle, it would not be found by the SZ effect or by X-rays because it is too faint. It's high energy signal. We also talked about protocluster here, G191, also selected in the same way by being ultra bright in the submillimeter as a result of its high star formation rates. Okay. Both of these sources are interesting because they'll be observed in guaranteed time using JWST. These two and another 5 clusters, some of which are found by these sort of unconventional techniques. Okay, and I'll put up my summary slide and end my talk there. So I hope I didn't.
Hard to do applause online.
There is an applause icon, but you don't have to. You're not obligated to applaud me. By the way, I'm very, very happy to talk about these sources. So.
Well, I'm not sure where the icon is, but we'll take it as as assumed to be happening.
Okay, sure.
Applause on my own table. Thank you for that.
Absolutely.
Nice overview. Very good. Everybody's laughing. I've
Cheers.
got my thing so that I hold down the button to unmute myself, but if I'm doing that, then I can't clap. And James has clapped in the chat window anyway.
Mm,
James Taylor. So,
thank
question.
you.
I guess you could use the raise hand thing or just call out if, and we'll see. Try just calling out first. We'll see if if that works. Questions, people? Gazal, did you have your hand up earlier? I thought I saw that flash.
Yes,
Sure.
just like it's the reason you were saying Planck cannot do one field IR galaxy. Is it not sensitive enough? What is the reason?
Right. Yeah. Yeah. That's right. Yeah. Yeah. It lacks the sensitivity to detect single sources in the field. Yeah. Which is why you don't hear about doing astronomy usually. Usually, it's not your choice for doing astronomy.
Just because the beam is too large.
The beam is very large. Yeah.
Nice. Okay.
In fact, the beam is so large that if you're a galaxy cluster pundit, you might actually realize that you can't actually detect high redshift clusters using Planck only, either using Planck as that effect, actually. But most people don't know that, so I still put that into every talk because of the beaming effect.
I see. Okay. Thank you.
Other questions? I'm scrolling up and down the list. I can't.
I was going to ask about your the detections, the maps where you showed multiple sources. Could you just go over those? Because I can never tell the difference between the sources and the
Yes.
noise peaks.
Sure. Okay. Let me see. Okay. So you meant the Herschel sources. Do you mean these?
Yeah, that's
Yes.
right. That's right.
Yes.
So how many things? Which things in those are real sources, and how big are the sources?
Yeah. So thanks for asking. So it turns out. So let me first point out a bit more then. So once again, just so you know, there are only two sources shown here. This upper one, G256, is shown in 3 bands. And this lower one, G244, is shown in 3 different bands. So these are only 2 sources, one source and second source. Secondly, this white, you see this white contour in this image here and this one here. Those contours represent the 50% intensity contour of the light from the Planck detection. Okay, so what I'm showing is Herschel data, but with the Planck 50% intensity region marked. Okay, so 50% of the light from the Planck detection falls within the circles here and here, and here and here. Okay, so what we're really counting then is to try to see, is there an overdensity of sources within the Planck beam? Although there can be larger scale structures too, as might be the case here. Okay, so then now what Herschel reveals really is that there's not just one blob within this white beam, although there is here, but instead, it breaks up into several sources. Right. Okay.
So you would see six or 8 or maybe or something of those obvious white blobs.
Right. Well, these are also incredibly low resolution images relative to what you might expect, depending on which waveband that you typically work in, if you're an observer. So yeah, they're already. This source here, is that one source or a few? It's very odd if it's a single source, and if it's a single source at redshift 2.5, what's it doing with that odd shape? That's probably some merging thing. The same here. What is that? Is that one source, 2, 3? Right, we don't know, but we can count the numbers of separately detected sources, and there are about 5 to 10 separately detected sources within the Herschel beam, but that's a lower limit on the actual number. If that helps.
Yeah, it's just funny because, for instance, there the morphology changes quite a lot from 250 to 350 and 350 to 500. I mean, if I superpose those maps, with some things it would line up, and then with other things, the blobs seem to change or move around a lot.
Yeah, so remember, we are selecting by these colors, actually. So we do expect for there to be differences between these bands. And we expect that what we're seeing here is the change in the thermal distribution of the dust emission. So yeah, you do see some differences. I don't see a lot of differences, but this is why I love giving talks, because one can also see something better if you don't look at it every day. But look, I see this concentration here, which is the same for all three. I see these two sources, you see those two, which are the same there and the same there. And I see this kind of, whatever it is, L shape, which is there and there and there. It looks the same to me. What is, I mean, or do you just mean that in detail, maybe this one here, you can't really exactly reproduce there, right? And that doesn't look exactly the same as that.
Yeah, exactly. It's more the stuff in the 500 micron image towards the bottom. You know, it's much, much brighter. And so I would guess that if it's a protocluster, they should all have similar colors in the submillimeter, or is it something where the colors can also vary because of star formation rates or things like that?
The colors will vary, but between. Okay, so here we show a nice plot that might help answer your question. These are the 500 micron over 350 micron colors of what I just showed, the Herschel Spire colors. Okay, versus the 250 versus 350 ones. Here are all of our 228 sources. So they follow, you know, they do have a spread of color for sure into their different properties or whatever, but they're not also completely randomly splayed out over this plot of color space.
Yeah, I mean, I'm just thinking at a single redshift. So if I imagine taking a single cluster of objects at some redshift, so I guess that would be like a kind of diagonal band across this, or it would be at one color on your color, your coloring of that plot.
Yeah, right. It should be a much more narrowly defined distribution if it's in a single redshift slice. Yeah, I think that's true. The main difference coming about as a result of this effect, right? So that we expect to see a sort of a color difference as a result of the pseudo-thermal spectrum. Yeah.
Good. Other questions?
Yeah, so I can ask something. Like, you know, so for the caustic crossing stars you mentioned, Brenda.
Yeah.
So you mentioned, you know, that the magnification was like 10,000 or something. Is that right?
No, magnification factors can achieve 10,000. That's not the case. For the very first detection of Icarus, remember the one I showed on the very first slide of that part of the talk, the estimated magnification factor was up to 2,000. Okay, that was this one here. And for this one here, for our flux ratio approach, we measure, I think it's a factor of 300.
Oh, okay, I see. Okay. It's like hundreds, but not like tens of thousands.
No.
Oh, okay,
that's
sorry.
Right.
I was confused.
But a minimum of a factor of 10 greater than anything that can be achieved by cluster lensing, which is enough to get my attention anyway.
Okay.
I'm sure the numbers worked out, but it seemed a bit surprising to me that a single star, even multiplied by a factor of 300, would have a significant effect on the overall light, I guess. But
yeah, well, interestingly, not only did it work out, but it worked out independently twice. So I mentioned our paper, Frye et al. 2019, and really within days, a different paper by Chen et al. 2019 was submitted. And I remember right before they were submitted, I was at a conference talking to someone from the other team, and I thought at first we had made the same discovery, but it turns out that we made the discovery of a source by this flux ratio method I described, you know, using this Picasso icon here, of a brightening of a source in 2014. And Chen et al. Made the discovery of a caustic crossing event, but at a different epoch and using a different method, using just a difference imaging method. So we have completely different detections. In fact, we weren't competing at all. Completely independent detections in different sources. And somehow I think the referee made reference to it. I think maybe the editor or someone pointed them to these other papers. So it's very interesting.
So I'm trying to remember my Hertzsprung-Russell diagram, and I know where the blue supergiants are, but I can't remember where they would be on the luminosity axis.
Yeah, no, it's a very good point, because me and my colleagues who wrote this paper here were very similar state. So blue supergiants are about the most commonly expected caustic transit that one could try to detect with HST, because they're the most luminous things. So are red supergiants, but we have no sensitivity to detect them until JWST is launched.
But how bright are they? Compared to like the sun's brightness?
Well, that's a really good point, and that's why we're at a kind of seminar setting. Is there anyone who could help me out here?
4.
There you go.
-4.
So for those of us who don't know what magnitudes are, can you?
Now, I do have to point out that Chen et al. Made their detection by a completely different method, and so they have a completely different magnification factor, which may also be very correct, because these caustics are changing and complex, and they had a magnification factor that's a factor of 3 or 4 higher than ours. So
Was a different caustic, I guess, right? I mean, because it's
yes, definitely,
so
definitely. It was in a different epoch,
Same.
even, in which they made their, yeah. So they're, yeah.
So I don't know. Would a blue supergiant be 1,000 solar luminosities?
Yes. I mean, I think they go up to roughly, 1,000 to a few thousand.
I'm just guessing. I don't really
Yeah.
know.
I mean, what's
this galaxy presumably has like, I don't know, like billions of stars in it, right?
Yes, this galaxy is at redshift 0.94, I think. So it's what you expect of galaxies at redshift. We have a lot of galaxy evolution experts, I think,
It's an
at
L-star-like
this
galaxy.
seminar. Pardon?
It's an L-star, sort of
Yeah.
a typical L-star.
Right.
Galaxy.
It might be. It's a star-forming galaxy. I don't know a lot about the actual galaxy, but it it doesn't
If
look
its
like.
magnification is just like 10 times higher than everyone else's magnification in that galaxy, then it's still kind of surprising to notice that one star, right? So is it possible for something else to be causing this variability? Like, is it possible for like a nova or a AGN or something to be causing the variability?
AGN, no. We certainly have constraints, sufficient constraints to know it's not an AGN. Although it's a very nice idea. With the really fortuitous geometry, we could potentially sample really close into a galaxy center, but that's maybe a different topic. And could it be a nova or something? I suppose there must always be, uncertainties in this type. It's very blue. It's very blue. I don't know exactly what we expect from a nova, but I wasn't able to go into detail showing it all. You can look up Kautoff et al. 2019. It's very, very blue.
Mm-hmm.
Okay.
How many pixels is the image in area?
Yeah, well, that's a really good point. You can see a close-up of this face here, which I show in this slide in the upper left. I mean, yeah, I should have, we could have made this plot of image ribbon F with, sort of a histogram style instead of the smooth style, so you could be able to count that up yourself. But there would be roughly 20 or 30.
Across.
Yeah.
So it's
along the long axis.
Yeah, so it's 400 in area. No,
Oh,
I'm just.
Sorry, you can't. Oh, sorry. You can kind of see the pixelation.
Yeah, I'm just thinking for magnification. I mean, depending on exactly what you're measuring, it may be a question of, how bright is that one star relative to all the stars in the pixel it's in. So that's then a 400th or whatever of the galaxy brightness, roughly, right?
Yeah.
So that helps you a little bit.
Yep.
Yeah, that's true. Yeah.
Good. I think we've run over a bit, so we should probably wrap up. I found, at least on Zoom, there's a reactions thing, and it has a clapping option. So I'm gonna do that one.
It's okay. All right. Okay. Thank you. Yeah. No, it's really nice to have the chance to do this. So
Yeah,
take
it's
on
to
this,
keep
this
the
topic.
science alive while everything else is sort of a little
Thanks
bit
very much. A very nice talk.
suppressed.
Thank you. Thank you. I appreciate it. Yeah. Yeah.
And
Look forward to next time.
I would encourage people on Zoom, for future talks. Most of you have your full name, but I didn't know BRM was Brian McNamara until
Mm,
he just spoke. So,
that's true.
I'd
Yeah.
encourage you to put your full names on so everybody knows, including the speaker. Maybe they recognize the name when the
Right.
question's
Right.
asked.
Exactly. Yeah. Or some people put icons on it, have a little picture of themselves or something.
Their
And
hand.
that
Well, I would